Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The year 1347 marked the beginning of humanity's darkest chapter. Across the vast expanse of Eurasia, a microscopic killer began its relentless march, leaving devastation that would reshape civilizations. The Black Death, as history would remember it, claimed between 75 and 200 million lives. Nearly half of Europe's population vanished within just 5 years. But this catastrophe wasn't merely a biological disaster. It was intimately connected to Earth's climate system in ways that scientists are only now beginning to fully understand. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Modern paleoclimatology reveals that the 14th century witnessed extraordinary atmospheric upheaval. Tree ring chronologies from across Europe and Asia show dramatic growth anomalies beginning in the 1320s, indicating severe climate stress. Ice core data from Greenland confirms this period as one of the most climatically volatile in the past 2 millennia. These natural archives tell a story of unprecedented weather extremes that created perfect conditions for pandemic emergence. The relationship between climate and disease transmission operates through complex feedback mechanisms. Temperature fluctuations directly affect pathogen survival rates, while precipitation patterns influence vector populations and human agricultural systems. During the 1340s, Europe experienced what climatologists now recognize as the onset of the Little Ice Age, a period of cooling that would persist for centuries. Contemporary chronicles describe the unusual weather with remarkable consistency. The Annales Gandenses record summers so wet that grain rotted in the fields, while winters arrived with such ferocity that major rivers froze solid for months. Italian chronicler Giovanni Villani documented temperature drops so severe that olive groves died throughout Tuscany. Trees that had thrived for generations suddenly succumbed to unprecedented cold. These weren't isolated incidents but manifestations of broader atmospheric reorganization. Volcanic eruptions in 1343 and 1348, including a massive eruption in the Kuwait caldera, injected millions of tons of sulfur dioxide into the stratosphere. This volcanic aerosol veil reflected incoming solar radiation, triggering global cooling that persisted for decades. The plague bacterium Yersinia pestis thrives within specific temperature and humidity ranges. Laboratory studies demonstrate that its transmission vectors, primarily rat fleas of the species Xenopsilla chiopis, exhibit peak activity at temperatures between 68 and 78 degrees Fahrenheit, with humidity levels above 60%. The climate disruptions of the 1340s created these optimal conditions across vast geographical regions simultaneously. Agricultural collapse preceded the plague's arrival by several years. The Great Famine of 1315 to 1322 had already weakened European populations, making them more susceptible to disease. Malnutrition compromises immune system function, while social disruption forces human populations into closer contact with disease vectors. Climate-driven crop failures created refugees who carried pathogens across traditional boundaries. Trade networks, already stressed by economic instability, became superhighways for disease transmission. The Silk Road, connecting Asia to Europe through Central Asia, experienced unprecedented traffic as merchants sought alternative routes around failing agricultural regions. Ships carrying grain also carried rats, and with them, infected fleas that would seed new outbreak centers across the Mediterranean. This convergence of climate disruption, agricultural collapse, and enhanced connectivity created what epidemiologists call a perfect storm for pandemic emergence. The Black Death wasn't simply bad luck. It was the inevitable result of atmospheric, biological, and social systems reaching critical thresholds simultaneously. Understanding these connections provides crucial insights for modern pandemic preparedness in our rapidly changing climate. The relationship between volcanic eruptions and plague outbreaks reveals one of nature's most devastating feedback loops. Between 1343 and 1348, Earth's atmosphere absorbed an unprecedented burden of volcanic emissions. The Kauai volcano in present-day Vanuatu unleashed one of the largest eruptions of the past millennium, ejecting approximately 32 cubic kilometers of material into the stratosphere. This catastrophic explosion created what climatologists term a volcanic winter, but paradoxically, these cooling conditions proved ideal for bacterial proliferation. Volcanic aerosols operate as atmospheric thermostats, reflecting incoming solar radiation back to space, while simultaneously trapping long-wave radiation near Earth's surface. Ice core analysis from both Greenland and Antarctica shows sulfuric acid spikes corresponding to the 1340s eruptions, with concentrations exceeding background levels by more than 400%. These chemical signatures provide precise dating for the climate disruption that preceded the Black Death. The cooling effect wasn't uniform across the globe. Northern Europe experienced temperature drops of 2 to 3 degrees Celsius, while Mediterranean regions saw more modest but still significant cooling of 1 to 2 degrees Celsius. This differential cooling created unique atmospheric circulation, patterns that would prove crucial for disease transmission. The jet stream, weakened by reduced temperature gradients, meandered more extensively, creating persistent weather patterns that lasted weeks or months. Yersinia pestis exhibits remarkable sensitivity to environmental conditions. Modern laboratory studies demonstrate that the bacterium's growth rate doubles when temperatures drop from 82 to 73 degrees Fahrenheit, precisely the temperature range created by volcanic cooling in 14th century Europe. Additionally, the pathogen produces a biofilm blocking mechanism at temperatures below 73 degrees Fahrenheit, making infected fleas unable to properly digest blood meals and forcing them to attempt repeated feeding, thereby increasing transmission rates. The volcanic winter created ideal humidity conditions through altered precipitation patterns. Cooling atmospheric temperatures increased relative humidity even without additional moisture, while disrupted circulation patterns brought unusual rainfall to typically dry regions. Tree ring analysis from Central Asian sites shows dramatically increased growth during the 1340s, indicating abundant moisture availability in regions that typically experience arid conditions. These environmental changes affected not just the plague bacterium, but its entire transmission complex. Rattus rattus, the black rat that served as the primary plague reservoir, thrives in moderate temperatures and high humidity. Archaeological evidence from European urban sites shows rat populations peaked during the cooler, wetter conditions of the mid-14th century. Simultaneously, grain storage became more challenging as increased moisture promoted spoilage, forcing closer contact between human food supplies and rodent populations. The volcanic cooling also disrupted traditional seasonal patterns that had previously limited plague transmission. Normally, summer heat would reduce flea survival rates and break transmission cycles. However, the cooler summers of the 1340s maintained optimal flea activity throughout what should have been unfavorable seasons. Contemporary chronicles describe summers so cool that crops failed to ripen properly, yet these same conditions extended the plague transmission season from typical 3-month windows to year-round activity. Atmospheric chemistry changes accompanying. Volcanic eruptions created additional biological stresses. Increased atmospheric sulfur compounds altered soil chemistry, affecting plant nutrition and subsequently the entire food web. Weakened vegetation provided poorer nutrition for herbivores, which in turn affected predator populations that normally controlled rodent numbers. This ecological cascade removed natural barriers to plague reservoir expansion. The Kauai eruption's timing proved particularly catastrophic, occurring just as trade networks had recovered from earlier 14th century disruptions. The volcanic winter struck when human populations were most vulnerable and interconnected. The combination of environmental stress, weakened immunity from poor nutrition, and enhanced pathogen transmission created conditions unparalleled in recorded history. Understanding. These volcanic plague connections provide sobering perspective on contemporary climate risks. Modern volcanic monitoring systems track dozens of potentially explosive volcanoes worldwide, while climate models predict how future eruptions might interact with anthropogenic warming. The 14th century experience demonstrates that rapid climate changes, regardless of their cause, can trigger cascading biological and social disasters whose effects persist for generations. The Asian monsoon system, Earth's most powerful seasonal atmospheric circulation, became the unwitting architect of plague transmission across the world's largest continent. Volcanic cooling from the 1340s disruptions fundamentally altered this massive weather engine, creating a cascade of ecological and social changes that would facilitate the Black Death's eastward spread. The monsoon's failure didn't just bring drought, it reconfigured the relationship between humans, animals, and pathogens across vast regions of Asia. Monsoon systems depend on temperature contrasts between land and ocean masses. During normal years, intense solar heating of the Asian landmass creates low-pressure zones that draw moisture-laden air inland from the Indian and Pacific Oceans. However, volcanic aerosols reduced incoming solar radiation by approximately 2 to 3% globally, with even greater reductions over continental interiors. This cooling eliminated the thermal gradients that drive monsoon circulation. Chinese historical records provide detailed documentation of the monsoon's failure. The Yuan dynasty chronicles describe successive harvest failures beginning in 1343, with some regions receiving less than 30% of normal rainfall for 5 consecutive years. The Yellow River, typically swollen by monsoon rains, reached historically low levels, forcing millions of Chinese farmers to abandon traditional agricultural areas and seek survival elsewhere. These human migrations created unprecedented opportunities for disease transmission. Archaeological evidence from Central Asian sites shows dramatic population increases in oasis communities during the 1340s as refugees from drought-stricken regions concentrated around remaining water sources. These population densities, far exceeding historical norms, brought humans into closer contact with established rodent colonies that harbored plague bacteria. The disrupted monsoon created what epidemiologists term sylvatic plague conditions, situations where wild rodent populations become primary disease reservoirs. Marmot colonies across the Central Asian steppes, stressed by prolonged drought, began dying in massive numbers. Contemporary Chinese medical texts describe travelers finding thousands of dead marmots along traditional trade routes, a phenomenon modern science recognizes as plague epizootics among wild rodent populations. Silk Road trade networks, already disrupted by political instability, faced additional challenges from climate-driven ecological changes. Traditional water sources along caravan routes disappeared or became unreliable, forcing merchants to use alternative pathways that brought them into contact with infected rodent populations. Caravanserai, the fortified roadside inns that served long-distance traders, became inadvertent mixing centers where human travelers, their animals, and local rodent populations intersected. The plague bacterium's survival strategy exploited these new ecological relationships. Yersinia pestis can persist in soil for extended periods under appropriate conditions, and the combination of cooling temperatures and altered precipitation patterns created ideal soil environments across Central Asia. Dead rodents became bacteria reservoirs that could infect new hosts. Months after initial die-offs occurred, climate disruption also affected the vectors that transmit plague between rodent and human populations. Flea species exhibit different temperature tolerances and feeding behaviors. The cooling conditions favored Xenosylla chiopes, a flea species particularly effective at transmitting plague to humans while reducing populations of other flea species that rarely bite humans. This selective pressure effectively concentrated plague transmission potential in the most dangerous vector species. Maritime monsoon failures had equally devastating effects on ocean-based trade networks. Reduced seasonal winds made sea voyages longer and more unpredictable, forcing ships to make extended stops at ports where they previously would have paused briefly. These extended port stays increased opportunities for rats to move between ships and shore communities, carrying infected fleas across vast oceanic distances. The monsoon's betrayal created feedback loops that amplified plague transmission for decades, Weakened agricultural systems couldn't support normal population levels, forcing permanent changes in settlement patterns that brought humans into closer contact with wild animal populations. Traditional ecological knowledge that had previously helped communities avoid plague exposure became obsolete as environmental conditions shifted beyond historical experience. Recovery from monsoon failure required generations rather than years. Tree ring data from Mongolian sites shows reduced growth continuing into the 1360s, indicating that climate disruption persisted long after the initial volcanic triggers. This prolonged ecological stress maintained conditions favorable to plague circulation, explaining why the pandemic continued to flare up repeatedly across Asia throughout the later 14th century. Modern climate science recognizes monsoon systems as particularly vulnerable to rapid environmental changes. Contemporary research suggests that 21st century warming could disrupt monsoon patterns with similar devastating effects, potentially creating new opportunities for zoonotic disease emergence across regions home to billions of people. While Asia suffered from drought, Europe endured the opposite extreme: unprecedented rainfall that transformed cities into disease incubators. The same atmospheric disruptions that weakened Asian monsoons intensified European precipitation patterns, creating urban environments perfectly suited for plague transmission. Medieval cities, already struggling with sanitation challenges, became death traps when climate change overwhelmed their primitive infrastructure. European weather records from the 1340s describe rainfall totals that exceeded normal levels by 50 to 100% in many regions. The Chronicle of Giovanni Villani records Florence receiving continuous rain for over 60 days during the summer of 1348. Weather patterns so unusual that chroniclers interpreted them as divine portents. This excessive moisture created cascading problems that would prove fatal when plague arrived. Urban infrastructure in 14th century Europe couldn't handle such extreme precipitation. Most cities relied on simple drainage systems that emptied into rivers or constructed channels. When rainfall exceeded capacity, these systems backed up, flooding basements, cellars, and ground floor spaces where poor populations lived. Standing. Water became breeding grounds for disease vectors, while forcing humans and rodents into shared refuges on higher floors. The flooding had devastating effects on urban rodent populations, ironically creating conditions that enhanced plague transmission. To humans, as water levels rose, rats abandoned their normal underground habitats and sought shelter in human dwellings. Archaeological evidence from London shows dramatic increases in rodent remains in residential contexts during the mid-1400s, indicating unprecedented human-rodent proximity. Food storage systems, crucial for urban survival, became plague transmission networks. Medieval cities stored grain in cellars and ground-floor warehouses, precisely the areas most affected by flooding. Wet grain attracted larger rodent populations, while spoilage forced people to venture into contaminated storage areas more frequently. These interactions created countless opportunities for flea transmission between rodent and human hosts. The relationship between moisture and plague transmission operates through multiple biological pathways. High humidity extends flea survival rate significantly. Laboratory studies show that Xenocilla chaopis fleas live 3 times longer at 80% humidity compared to 40% humidity. European cities during the 1340s experienced prolonged periods of near-saturation humidity, creating optimal conditions for flea populations. Urban construction methods amplified these humidity effects. Medieval buildings typically featured organic materials, timber frames, thatched roofs, and earthen floors that absorbed and retained moisture. Once wet, these structures remained damp for extended periods, maintaining the high humidity levels that favor both flea survival and bacterial growth. Modern archaeological investigations of 14th century building remains show evidence of extensive moisture damage and mold growth. Population density in medieval cities created additional multiplication factors for plague transmission. Cities, like Paris, with estimated populations exceeding 200,000 people, packed residents into spaces that would be considered overcrowded even by modern standards. When flooding forced even closer proximity, transmission rates accelerated exponentially. Mathematical models suggest that transmission rates in crowded, humid conditions could be 10 times higher than those in dry, dispersed populations. The urban economy itself became a transmission network. Craft workshops, markets, and taverns, the economic heart of medieval cities, operated in ground floor spaces that were most affected by flooding. People couldn't avoid these contaminated areas because their livelihoods depended on continued economic activity. Contemporary accounts describe markets continuing to operate even as bodies accumulated in nearby streets, creating scenes of horrific juxtaposition between commerce and catastrophe. Sanitation systems that had functioned adequately under normal conditions completely failed during the extended wet period. Latrines overflowed, waste disposal systems backed up, and normally separate water supplies became cross-contaminated. These conditions created what epidemiologists recognize as syndemic situations, multiple disease threats operating simultaneously in the same populations. The cooling effects of volcanic activity combined with increased precipitation to create what some historians call nuclear winter conditions in European cities. Summers were so cool and wet that normal social patterns broke down. People spent more time indoors in close proximity, heating systems operated continuously, and ventilation was reduced, all factors that enhanced airborne disease transmission. Recovery from urban plague required fundamental changes in city design and public health policy. Many cities that suffered the worst mortality during the Black Death implemented new building codes, improved drainage systems, and enhanced waste management practices. These innovations, born from catastrophic experience, laid groundwork for the urban planning principles that would eventually make cities more resilient to both climate extremes and disease outbreaks. Understanding these historical urban climate disease interactions provides crucial insights for modern pandemic preparedness, particularly as climate change brings new extremes to contemporary cities, with populations far exceeding anything medieval Europe could have imagined. The Black Death's devastating mortality rates cannot be understood without examining the profound nutritional crisis that preceded and accompanied the pandemic. Climate disruption didn't just create optimal conditions for plague transmission, it systematically undermined human immune systems through widespread malnutrition, creating populations uniquely vulnerable to infectious disease. The relationship between nutrition and immunity reveals how environmental changes can weaken biological defenses across entire continents. Agricultural systems across Eurasia faced unprecedented challenges during the 1340s. Volcanic cooling shortened growing seasons by 3 to 4 weeks in many regions, while altered precipitation patterns disrupted traditional planting and harvesting cycles. Crop yields declined by 30 to 50% across Europe, with some regions experiencing near-total harvest failures for consecutive years. These weren't isolated famines, but systematic agricultural collapse affecting millions of people simultaneously. Malnutrition operates through complex mechanisms that compromise immune function at cellular levels. Protein deficiency reduces antibody production and impairs white blood cell function, while vitamin deficiencies affect tissue repair and inflammatory responses. Contemporary medical treatises, including works by physician Guy de Chauliac, who survived the plague in Avignon, describe populations exhibiting classic signs of severe malnutrition: hair loss, skin lesions, delayed wound healing, and increased susceptibility to minor infections. The specific nutritional deficiencies created by crop failures had particular relevance for plague mortality. Vitamin C deficiency, common when fresh vegetables became unavailable, impairs collagen synthesis and weakens blood vessel walls, factors that would exacerbate the hemorrhaging associated with bubonic plague. Iron deficiency anemia, widespread during famines, reduces oxygen carrying capacity and compromises cellular energy production needed for immune responses. Social responses to famine created additional pathways for disease transmission. As food supplies dwindled, Traditional social structures broke down. People abandoned villages to seek opportunities elsewhere, creating refugee populations that carried diseases across geographical boundaries. Urban centers, already strained by their own agricultural shortfalls, found themselves flooded with malnourished rural populations seeking survival opportunities. The grain crisis also affected food preparation and storage practices in ways that enhanced disease transmission. Desperate populations consumed foods they would normally avoid: spoiled grain, unusual plant materials, and even deceased animals found in fields. These dietary changes exposed people to additional pathogens, while their weakened immune systems struggled to cope with increased microbial loads. Children and elderly populations suffered disproportionately from nutritional stress, creating demographic vulnerabilities that plague would exploit ruthlessly. Historical demographers estimate that child mortality rates increased by 200 to 300% during the famine years preceding the Black Death. When plague arrived, these age groups, already weakened by malnutrition, experienced mortality rates approaching 90% in some communities. The relationship between malnutrition and plague created feedback loops that amplified mortality rates. Malnourished populations were more likely to develop severe plague symptoms, which reduced their ability to care for others or maintain basic sanitation. As mortality rates increased, agricultural labor forces declined, perpetuating food shortages and maintaining the nutritional crisis that made populations vulnerable to continued plague transmission. Economic responses to the grain crisis inadvertently facilitated disease spread. Authorities attempted to maintain food supplies by importing grain from distant regions, creating new trade networks that carried infected rodents across previously separate disease pools. Ships carrying emergency grain supplies also carried rats and fleas that would seed new plague outbursts in recipient ports. The nutritional crisis had lasting effects that extended well beyond the immediate famine period. Populations that survived the grain shortages of the 1340s remained immunologically compromised for years, making them vulnerable to the repeated plague outbreaks that characterized the later 14th century. Tree ring data suggests that agricultural productivity didn't fully recover until the 1370s, meaning that nutritional stress continued for an entire generation. Modern nutritional science confirms the historical relationship between malnutrition and infectious disease mortality. Contemporary studies show that malnourished populations experience infection rates 3 to 5 times higher than well-nourished groups, with case fatality rates that can be 10 times greater. These multipliers help explain why the Black Death achieved mortality rates that seem almost impossible by modern standards. The grain crisis also reveals how climate change can create rapid social transformations that persist long after environmental conditions normalize. Communities that lost substantial portions of their population to combined famine and plague were forced to reorganize economic and social systems fundamentally. Many villages were abandoned entirely, while survivors concentrated in new settlement patterns that would characterize European demographics for centuries. Understanding these nutrition-immunity-climate connections provides crucial insights for contemporary global health security, particularly as climate change threatens agricultural systems that currently support billions of people who could face similar vulnerabilities if food security fails on a massive scale. Climate change in the 14th century didn't just create local conditions favorable to plague transmission, it fundamentally altered the global networks that connected distant populations, turning trade routes into superhighways for pandemic spread. The same atmospheric disruptions that brought drought to Asia and flooding to Europe also changed wind patterns, ocean currents, and seasonal weather cycles that determined how goods, people, and pathogens moved across continents and oceans. The Silk Road, humanity's first truly global trade network, experienced unprecedented disruption during the 1340s. Traditional caravan routes depended on predictable seasonal patterns that provided water, fodder, and favorable weather for long-distance travel. Volcanic cooling altered these patterns dramatically, forcing merchants to use alternative pathways that brought them into contact with plague-infected rodent populations in regions previously avoided. Central Asian oasis cities became crucial, transmission nodes where multiple trade routes converged. Cities like Samarkand and Bukhara, already important commercial centers, found their significance magnified as climate disruption forced merchants to use concentration points rather than dispersed routes. Archaeological evidence shows dramatic population increases in these cities during the 1340s, creating precisely the crowded conditions that favor rapid disease transmission between human and rodent populations. Maritime trade networks faced equally significant disruptions from changing atmospheric circulation patterns. The monsoon systems that powered Indian Ocean commerce became unreliable, forcing ships to spend extended periods in ports while waiting for favorable winds. These prolonged port stays created opportunities for rats to move between ships and shore communities, establishing new plague reservoirs in coastal cities that had previously remained isolated from continental disease pools. Wind pattern changes affected more than just travel times. They altered the fundamental geography of global commerce. The jet stream, weakened by reduced temperature gradients, meandered more extensively, creating persistent high and low pressure systems that blocked traditional shipping routes while opening new pathways. Mediterranean trade, crucial for connecting Asian and European markets, experienced route changes that brought ships to previously secondary ports where plague surveillance and containment were minimal. The Black Sea became a particularly crucial transmission pathway due to climate-driven changes in regional wind patterns. Genoese and Venetian merchants, seeking alternatives to disrupted overland routes, increased their reliance on Black Sea commerce to connect with Asian trade networks. The city of Kaffa, modern-day Feodosia in Crimea, became a critical node where Asian plague strains first entered European trade networks. Climate change also affected the seasonal timing of trade activities in ways that amplified disease transmission. Traditional trading seasons were based on predictable weather patterns that minimized travel risks while maximizing cargo capacity. Disrupted seasons forced merchants to travel during periods when disease vectors were most active, while unpredictable weather patterns kept ships and caravans in close quarters for extended periods. The emerging Atlantic trade networks, still in their infancy during the 14th century, provided new pathways for intercontinental disease transmission. Portuguese and Spanish maritime explorations, initially focused on finding alternatives to disrupted Asian trade routes, inadvertently created connections between previously isolated disease pools. While the major impacts of these connections wouldn't be felt until later centuries, the foundation infrastructure was established during the climate chaos of the 1340s. Urban port cities became amplification centers where local and international disease transmission intersected. Cities like Constantinople, Venice, and Genoa served as interfaces between overland and maritime trade networks, creating mixing zones where pathogens from multiple geographical origins could interact and potentially recombine. The genetic diversity of plague strains recovered from 14th century European sites suggests extensive mixing of Asian and local bacterial populations. The speed of plague transmission across trade networks exceeded anything previously seen in human history. Contemporary chronicles describe plague appearing in cities separated by thousands of miles, within weeks of each other, transmission rates that would have been impossible without the enhanced connectivity created by climate-disrupted trade patterns. Mathematical models suggest that plague spread along major trade routes at speeds of up to 50 miles per day, far exceeding the pace of human travel. Economic desperation caused by climate disruption also intensified trade activities in ways that facilitated disease spread. As local agricultural systems failed, communities became more dependent on imported goods, increasing the frequency and intensity of long-distance commerce. This economic pressure forced continued trade activities even as plague mortality became apparent, creating situations where economic survival required accepting disease transmission risks. The transformation of global trade networks during the Black Death period established patterns that would persist for centuries. Many alternative routes opened during the 1340s became permanent features of global commerce, while traditional pathways that proved vulnerable to climate disruption were gradually abandoned. These changes laid groundwork for the early modern global economy, while demonstrating how environmental pressures can rapidly reshape human connectivity patterns. Understanding these historical trade-climate-disease interactions provides crucial insights for contemporary global health security, particularly as climate change and economic globalization create new vulnerabilities in our vastly more connected modern world. The Black Death's conclusion didn't end its climate connections, it created lasting transformations that would shape human civilization for centuries. The pandemic's demographic catastrophe, amplified by climate disruption, triggered social, economic, and environmental changes whose effects remain visible today. Understanding these long-term consequences reveals how climate-driven disasters can fundamentally alter the trajectory of human development across multiple generations. Population collapse created entirely new ecological relationships across Europe and Asia. With mortality rates reaching 50 to 70% in many regions, vast agricultural areas returned to wilderness. Forest recovery, documented through pollen analysis and historical records, dramatically altered regional carbon cycles and local climate patterns. This reforestation may have contributed to the continued cooling that characterized the Little Ice Age, creating feedback loops between demographic collapse and climate change. The social transformations triggered by climate-amplified plague mortality revolutionized European economic systems. Labor shortages empowered surviving workers to demand higher wages and better working conditions, beginning the breakdown of feudal agricultural systems. The Peasants' Revolt of 1381 in England and similar uprisings across Europe reflected new social dynamics created by demographic scarcity. These changes accelerated the transition toward monetary economies and urban-based commerce that would define the late medieval period. Technological innovation accelerated as societies sought to overcome labor shortages through mechanical solutions. The widespread adoption of windmills, watermills, and agricultural improvements like the heavy plow reflected adaptation to post-plague demographic realities. These technological changes increased per capita productivity while reducing human dependence on climate-sensitive agricultural systems, creating more resilient economic foundations. Medical understanding advanced rapidly as physicians confronted the unprecedented challenge of climate-amplified disease transmission. While medieval medical theory couldn't identify the bacterial cause of plague, practitioners developed more sophisticated understanding of environmental factors affecting disease spread. Concepts of quarantine, public sanitation, and epidemic surveillance emerged from Black Death experiences, laying groundwork for modern public health systems. Urban planning evolved to address the infrastructure failures revealed during the pandemic. Cities that rebuilt after plague devastation incorporated improved drainage systems, wider streets, and enhanced waste management, changes that reduced vulnerability to future disease outbreaks. These urban innovations, originally developed to address climate-disease interactions, became standard features of European city design. The psychological and cultural impacts of the climate plague catastrophe influenced European intellectual development for generations. The experience of witnessing environmental chaos linked to mass mortality contributed to changing attitudes toward nature, authority, and human vulnerability. These intellectual shifts would eventually contribute to the scientific revolution, as scholars sought better understanding of natural systems that could produce such devastating consequences. Religious institutions, initially strengthened by populations seeking divine protection from plague, ultimately faced challenges as environmental explanations for the catastrophe gained acceptance. The rise of naturalistic explanations for disease transmission, while still primitive by modern standards, represented important steps toward scientific approaches to epidemic control. This intellectual transition would prove crucial for future pandemic responses. Climate science benefits enormously from studying the Black Death period because it provides one of the best documented examples of rapid climate change impacts on human societies. Ice core data, tree ring chronologies, and historical records from this period offer detailed insights into how societies respond to sudden environmental shifts. These data sources continue to inform modern climate impact assessments and adaptation planning. The Black Death experience demonstrates how climate disruption can create cascading failures across multiple systems simultaneously. Agricultural collapse, demographic crisis, economic disruption, and social upheaval reinforced each other in ways that amplified the initial climate trigger. Modern risk assessment must account for these multiplicative effects when evaluating contemporary climate change threats. Contemporary pandemic preparedness can learn crucial lessons from the 14th century experience. The COVID-19 pandemic showed how rapidly modern global connectivity can facilitate disease transmission, while climate change creates new, environmental stresses similar to those that amplified the Black Death. Understanding historical climate-disease interactions helps identify vulnerabilities in modern systems and develop more effective prevention strategies. Modern zoonotic disease surveillance programs specifically monitor climate-sensitive transmission pathways identified through historical analysis of events like the Black Death. Programs tracking rodent populations, vector species distributions, and environmental conditions that favor pathogen transmission all reflect lessons learned from studying past climate disease interactions. The ultimate lesson of the Black Death's climate connections lies in recognizing the fundamental interconnectedness of Earth's environmental, biological, and social systems. Climate change doesn't operate in isolation. It triggers cascading effects that can amplify relatively small environmental shifts into civilization-altering catastrophes. The 14th century experience serves as both historical warning and contemporary guide for navigating the climate challenges that define our modern era. As we face unprecedented global warming, understanding how past climate disruptions facilitated pandemic emergence becomes crucial for protecting human populations from similar future threats. The Black Death reminds us that climate change isn't just an environmental issue. It's a comprehensive challenge that affects every aspect of human civilization, requiring integrated responses that address environmental, biological, and social vulnerabilities simultaneously. The whispers of cosmic forces that triggered the Black Death continue to echo through modern climate science, reminding us that planetary systems operate on scales and timelines that can overwhelm human preparations. By listening carefully to these cosmic whispers, we can better prepare for the climate-driven challenges that await our increasingly connected and vulnerable global civilization.